This is lecture 20 of Applied Statistics. I want to say hi to all my students at Bethel. I want you to know that I'm praying for you in the midst of this difficult time here in spring 2020, and also for other people who are watching this. We're going to do two main things in lecture 20, and I'm especially excited about the second part here. In the first part, we're going to talk about a general linear model example. So far, the examples we've done are, well, simple linear regression, a quadratic model, and a multiple regression model that had two explanatory variables, but it was linear in those variables. Here in the general linear model example, we will be doing multiple regression with two explanatory variables, but there's going to be a nonlinear term in the expression. It still is going to fit under the rubric of what we call a general linear model. Then the second part is linear algebra approach to least squares. So far we've talked about deriving the normal equations with calculus, taking partial derivatives, setting them equal to 0, and deriving the normal equations from that. However, you can put this in a broader context of problems in linear algebra, and you can derive the normal equations just using ideas from linear algebra. And the two key things that you need are the fact that the length of a vector, its norm, involves a sum of squares. That's one key. And the second key that you need is the idea of orthogonality, the fact that two vectors are perpendicular, orthogonal, when their dot product is 0. Here's the lecture plan. Again, two parts. The first part is this general linear model example. We'll talk about the setup of the linear model, and once again, I generate the example with Mathematica, and I'll show you the code. It's pretty similar to what I've shown you already. We'll jump pretty quickly to the design matrix. We won't try to rederive it, but jump to it quickly. From there, jump pretty quickly to the normal equations. We'll solve the normal equations with an inverse matrix and a multiplication. Then we'll look at the answer, the sample general linear regression equation. Then we move on to our second main topic, this broader context, linear algebra and least squares. And let me also say, you can even put this in an even broader context within more advanced linear algebra. I might hint at that in a future lecture. In that context of linear algebra, we're going to be looking at an inconsistent system of equations. We'll have 3 equations and 2 unknowns. It'll be a linear system. It will be inconsistent in the fact that it won't have a solution, but it will have a least squares solution. The geometric meaning is key. We'll look at the geometric meaning in terms of what's called the column space of the coefficient matrix, which is also the same thing as what's called the image of the corresponding linear transformation. The least squares solution idea will be related to the fact that the output vector that we are targeting, so to speak, will not be in the column space of the matrix. It will not be in the image of the linear transformation, but there will be a vector in that image that is closest to our target vector. And that would be the b hat that we will try to aim at with our least squares solution. That'll make more sense when we get there. Talk about the relationship to the orthogonality of vectors, which again means perpendicularity. The relationship to the normal equations, this is the punchline. How do you derive the normal equations from all this? And then we'll derive the answer. Okay, so let's set up the general linear model through an example. Let's suppose our model, first of all, in terms of the mean of the response variable, in terms of fixed values of the explanatory variables, x1 and x2. Notice that we have, well, a constant term, as usual, 2 linear terms, just like in the last lecture, lecture 19. Then we have a nonlinear term, beta 3 times x1 times x2. It's nonlinear in x1 and x2 because they're being multiplied. This would be a nonlinear term. But this is still going to fall under the rubric of a general linear model. Then the individual responses, we add in some probability, are the mean values plus an error term, where the error term has a certain distribution. They're all independent and identically distributed random variables with a common distribution that's going to be normal with a mean of 0 and a certain positive variance. This time I picked the variance to be 9. Previously we picked examples where the variance was 4, just to do something different. That would mean the standard deviation sigma is 3. This again is still linear, in spite of the nonlinearity in the mean equation with the x1 times the x2. It's linear in the unknown parameters. Beta 0, beta 1, beta 2, and beta 3 are all to the first power. We can still write the normal equations in matrix form, and linear algebra techniques can still be applied. It's the same general technique, in fact. This is an example of a general linear model. If we want, you don't have to do this, but if you want, you could introduce a new variable, z equals x1 times x2, and then write what you might call a fully linear equation where z appears to the first power. But you don't have to do that, okay? So it's still a linear model. What is the design matrix X and the observed value vector Y of observed values? Like before, the design matrix is kind of tall typically. The first column is going to be all ones. The second column is going to be all the x1 values that we have observed values of y for. The third column is going to be all the x2 values. And then there's going to be a fourth column that will be the product of x1 times x2. And here it is. So here's the general form here. And here it is for our particular example. Ones in the first column. These are the x1 values in the second column. They range from 1 to 3. These are the x2 values in the second column. They range from 1 to 4. These are actually the same x1 and x2 values as in lecture 19. And this fourth column is x1 times x2. Notice, for example, that 8 is 2 times 4, 9 is 3 times 3, etc. Okay, that is our design matrix. What about the observed values? Here they are. Where these numbers come from? They came from me running a simulation in Mathematica. I'm going to go ahead and show you the Mathematica code right now. As usual, I'm going to make these files available to people. So this is similar to the code that I've shown recently, I think in lectures 18 and 19. Here is our model. I picked values for beta 0, beta 1, beta 2, and beta 3. I picked beta 0, the constant term, to be 5, beta 1 to be 3, beta 2 to be 2, and beta 3, the coefficient of x1 times x2, to be -1. I decided to make a contour plot of this, which shows its output values, and I can hover over these level curves to see the output values. That's 11.31 there, for example. And I saw that it never went negative, which I was happy about. It gets down into the 5s there and up here. I was hoping for positive outputs is when I bring some randomness into play. I'm going to now generate random y data using random variate and normal distribution. So again, essentially, I'm taking x1 and x2 to be deterministic. There's no randomness there. But then I plug those into the mu equations, and then I add on the error term. That's what right here. Normal distribution with a mean of 0 and a standard deviation of 3. The variance is 9. Random variate just samples from that distribution. As x1 ranges from 1 to 3, x2 ranges from 1 to 4. As I've shown you before, when you enter this code over and over again, you get different outputs every time because it's doing simulation. But it's still consistent with this model. I went ahead and picked a particular run of output, and I called it fixed linear data. And to make it more easy to access for the fit command, I did some flattening at. So don't worry about what that means. Here's the key command you need to fit these data with this model. Notice in the curvy braces here I have a 1, an x1, an x2, and an x1 times x2 term. In effect, the model for mu is a linear combination of those basis functions where I re-emphasize the variables are x1 and x2. Fit does give me the linear model. For the sample data, I'm thinking this is sample data now. The mu equation is population, a population equation. This is sample data based on a sample of size n equals 12. So here it is. There's my sample regression equation, and then I can define that as a function of x1 and x2 that I'm calling y hat. And then I can make a graph. I'm not going to show you the graph right now. I'll come back to that later in the PowerPoint first. So that's where these numbers came from for the y. Okay, those were the outputs that I generated with mu plus the random variate. Therefore, I'm trying to work toward the normal equations. As we've talked about before, you want to calculate x transpose times x. In the general case here of this situation, without actually plugging the numbers in yet, here is x transpose, here is x. Where n I have not specified, so you see the dot dot dots. For our case, n would be 12. Again, this is x itself. That's the design matrix. 1's in the first column. x11, x12 through x1n in the second column. Those are the values of x1. for the n data points. Again, like I mentioned in the last lecture, this notation with the subscripts here is a little bit unfortunate in that as you go down this column, the subscript notation is sort of the opposite of what is usually done with matrices. We increase the second index. This column is the x2 values, x21 through x2n, okay, n of those. And these are their products. And here's the transpose. Switch the rows and columns. You can double check, take the time, pause the video, double check that this product, this times this, does equal this 4 by 4 matrix. This is a 4 by n matrix. This is an n by 4 matrix. The two n's match, so we can multiply them to get a 4 by 4 matrix that looks like this. With the data that I have, the x values in particular, this matrix turns out to be this one that you see here. We can maybe double check a few of these. 12 is what n is. That matches that. There were 12 data points. The sum of the x values is indeed 24. Why? Well, there were, well, let's go back to the previous slide. There are, these are the x values right here. There are 4 1s, 4 2s, and 4 3s. Okay? So you get 4 plus 8 plus 12 is 24. And that is the number that goes right here. Okay, you double check the other ones. Okay, I'll show you the X matrix again. You might want to pause it and write that down. Then I'm going to go back and show you the summations and show you the answer for X transpose times X. It's this. Double check these things. It's worthwhile to do. We also want to take X transpose times Y. In general, in this situation, you're going to get this 4 by 1 vector. For our data, that turns out to equal this. Take the time to check that too. Note also this is a 4 by n matrix times an n by 1 vector. The two inner n's match. You're going to get a 4 by 1, a 4-dimensional vector right here. And again, double check these numbers based on the y values that I showed you. So the normal equations, in general, are x transpose b equals x transpose times y, where x transpose for our example times x is this matrix, and y, x transpose times y is this matrix, this 4-dimensional vector. This is a 4-dimensional unknown vector that we want to solve for. And the method to solve for this, at least if you have technology to help you, is to multiply both sides of this equation on the left by the inverse of x transpose times x. Assuming it's invertible, it will be in this kind of situation, as long as you got at least two different x values. Okay, so go ahead and maybe you have technology to do that. I'm going to show you the answer as well. So b, what we're after, in general is equal to this. And by the way, the normal equations involving x, this design matrix, is nice because this is a lot easier to memorize than all those formulas involving the summations, right? Those are pretty hard to memorize. This is much better. That's why the matrix vector approach is so nice. So we take the inverse of this matrix, notice the -1 here, times the vector x transpose times y. It turns out the inverse of the matrix is this. You might want to use technology to confirm that. We multiply that times y. Here is x transpose times y, which are the values of the b's. These b, b0, b1, b2, b3 are our statistics that estimate beta 0, beta 1, beta 2, beta 3. Those are population parameters. These are sample statistics as observed values, not as random variables. So our answer, our sample general linear regression equation, is this one right here. Y hat equals, you can also write mu hat equals, approximately 2.7166 plus 4.24198 x1 plus 2.83406 x2 minus 1.73167 x1 times x2. Maybe write that down because I'm about to show you the Mathematica again to see that it is the same number. I'm trying to memorize these here briefly right now. Or we can maybe toggle back and forth. Oh, that's the spreadsheet. Here's the Mathematica. Is this the same thing that we got there? Yes, we see up to rounding, small rounding errors, they're the same. Okay? Pretty nice. As long as you have technology to, in this case, invert a 4 by 4 matrix, then it's pretty nice. If you have to do the 4 by 4 matrix inverse by hand, then it's not so nice. but still theoretically doable. All right, so now we're doing the second part of the lecture, and I really enjoyed making this part, and I hope you enjoy listening to this. I really like linear algebra, and I really like it when we can connect different math topics, in this case linear algebra, to statistics, which we've been doing already so far, but this is even better because it's in a more general setting. Typically, so we're talking linear algebra here, not statistics, though this does apply to the statistics. Typically, a system of linear equations with more equations than unknowns will be what's called inconsistent. It will have no solution. Here's an example. So here we have a system of linear equations, 3 equations, 2 unknowns, x1 and x2. If you try to solve this system for x1 and x2, you will not be able to find an answer. How do you confirm that? Well, you can solve it in terms of row operations of an augmented matrix. If you're rusty on what an augmented matrix is, here we have, again, we have 2 unknowns, x1 and x2, that their coefficients correspond to the 2 columns of this augmented matrix right there, the left 2 columns. The 1, the 2, the -1, the -3, and the 4 match the coefficients of x1 and x2 in each of these equations. And then to the right of that, in the last column, these numbers, 3, -4, and 2, match the right-hand sides. That's called an augmented matrix. It's different than a coefficient matrix. This part of the matrix, this 3 by 2 part, you might call capital A. That would be a coefficient matrix. I'm going to call the right-hand side of the system as a vector B. So I'm sort of creating a 3 by 3 matrix by smashing the 3 by 2 matrix A with the 3-dimensional vector B together, like this. Do row operations, which means you're trying to go to reduced row echelon form to solve for x1 and x2. And what happens if you try to do that in this case? Well, here's the first step, which is really 2 steps. Notice my notation here means this first thing says multiply row 1 by -2 and add it to row 2 and put the answer in row 2. Why? Because we're trying to get a 0 there in the spot of row 2. Multiply row 1 by -2. I'm going to get a -2 there. If I add -2 and 2, I get 0. So I can put the answer there. That's an example of a row replacement operation. That is a valid kind of operation to do to get an equivalent system, so to speak, to the original system. Another example of row operation I can do to get a 0 down here is to multiply row 1 by 3 and add it to row 3 and put the answer in row 3. That's what this notation means. The new matrix has zeros in those 2 spots, and the first row stays the same because I'm not making any changes to that. Let's double check these other numbers. 2 times -2 is -4, plus -1 is -5. -2 times 3 is -6, plus -4 is -10. Then with the other operation, 3 times 2 is 6, plus 4 is +10. And then 3 times 3 is 9, plus 2 is +11. So this would correspond to an equivalent system of equations, x1 plus 2x2 equals 3, -5x1 equals -5x2 equals -10, and 10x2 equals 11. Right away, maybe you see that the second and third equations of that are inconsistent, and that's what happens if you continue going on. If I now try to get a 0 here by multiplying row 2 by 2, adding to row 3 and putting the answer in row 3, -5 times 2 is -10, -10 plus 10 is 0. I get a 0 here, but I get something non-zero on the lower right. 2 times -10 is -20, plus 11 is -9. And as a system of equations, as an augmented matrix for a system of equations, this corresponds to a third equation, 0x1 plus 0x2 equals -9. In other words, 0 equals -9. That's a contradiction. This system is inconsistent. It has no solution. The logic behind this, which by the way many people don't spend the time to think about, is this. Starting with the system, by doing these operations, I'm saying if I assume this has a solution, if I assume the system has a solution, then the corresponding system for this will have a solution, and the corresponding system for this will have a solution, and that means this system has a solution, and it means 0 equals -9, but obviously 0 does not equal -9. And that's a contradiction. What does it contradict? It contradicts the assumption that this has a solution, and that's the logic behind why it has no solution. It's an inconsistent system. Okay, so what? Well, now we're going to move toward trying to find not the solution of the system, because the system has no solution, but an answer that's sort of closest to being a solution, what's going to be a least square solution. We can write the system in matrix/vector form like this, AX equals B, where A is now the coefficient matrix. This one right here, which is a 3×2 matrix. By the way, this notation just means the set of all possible 3×2 matrices with entries in R. It's an example of something called a vector space when you add matrices and when you multiply them by scalars. Just focus on the fact that it's 3×2 and the entries are real numbers. The target vector, the right-hand side here, B, is 3, -4, 2. This is inconsistent with the previous B notation, where B was the unknown vector that we tried to solve with the statistics. Here, B is the right-hand side vector. Okay, it was the last column of the augmented matrix. This is a three-dimensional vector. It's an element of R3, three-dimensional space. And X here is not a normal, it's not a design matrix, it's an unknown vector. It's an unknown two-dimensional vector, in fact. Think about why this makes sense. A is 3×2, 3 rows, 2 columns. You got to multiply by a 2×1 vector to get a 3×1 vector. The inner twos match. The answer is going to be 3×1, three-dimensional. The inconsistency of the system can be described in two ways that are helpful, okay? Though if you haven't thought about this kind of thing, if you haven't had linear algebra in depth, this is a little weird. The inconsistency of the system can be written in terms of what's called the column space of A. Here's the column space of A. It's the set of all linear combinations of the columns of A. These two three-dimensional vectors are the columns of A. 1, 2, -3, and 2, -1, 4. As the coefficients, the weights in front of these vectors, these numbers x1 and x2, vary over all real numbers, this defines what we call the column space of A. It's an infinite set. In fact, geometrically, it's a two-dimensional subspace of three-dimensional space, R3. What does that mean? Well, I'm not going to get into a ton of details other than to say, geometrically, it can be thought of as being a plane, a two-dimensional plane through the origin in three-dimensional space, and I'm going to show you a picture of it here in a second. B, the target vector, 3, -4, 2, is not in the column space. Why? Because the system was inconsistent. It cannot be written as a linear combination like this. Because really what a linear combination like this means is it really is another way to represent A times X. A times X, by definition, is a linear combination of the columns of capital A with the entries of X, x1 and x2, as the coefficients or weights in front of those column vectors. Okay? This is the set of all possible products, A times X, as the vector X varies over R2. Or in other words, as x1 and x2 vary over R. B is not in the column space because the system is inconsistent. It has no solution. Here's a visual. So this box represents a piece of three-dimensional space, R3. This bluish plane through the origin represents the column space of A. It's a plane. You see just a part of it here. It really goes on forever and ever in all directions. It's a two-dimensional plane through the origin. It is the column space of A. The vectors A1 and A2, which are supposed to represent these columns, this is A1 and this is A2, as arrows, if you put the start of the arrow at the origin, are in this plane. They are parallel to the plane. If you think of the vectors as being points, they would be the endpoints of these arrows when you put the bases at the origin. Those points are in the plane. The vector B that is the right-hand side vector is not in the plane. Draw it starting at the origin, its tip is over here. As a point, it's over there. It's not a part of this plane. It's not in the column space. Okay? So there's no possible x that will make ax equal b. You can think of this in terms of linear transformations as well. Linear transformation, call it t, from two-dimensional space to three-dimensional space. So this is the domain. Input vectors are two-dimensional, output vectors are three-dimensional, defined by this equation. T of x, this is function notation here, t of x equals a times x. That's matrix times a vector. Got again a 3 by 2 matrix times a 2 by 1 vector. X is two-dimensional. Gives t of x, a times x, to be a three-dimensional vector. The input x is two-dimensional. The output t of x, a times x, is three-dimensional. This is a linear transformation, which has got a lot of other facts that you can think about with linear transformations. I only want to focus on the idea of the image. The image is the column space. What is the image of a linear transformation, or the image of any function in general, is the set of all possible outputs. Some people call that the range. I like avoiding the word range. I like using domain, codomain, and image. There's also something called the kernel, which I won't get into. The image of t is the set of all possible outputs, t of x, as x ranges over the domain, R2. That is the same as all products a times x, as x ranges over R2. And by definition of what a times x is, just like I said on the last slide, that's the set of all linear combinations like this, where these two things are the columns of capital A, as little x1 and little x2 range over R, and that, like I said, is the same thing as the column space. It's just another way of thinking about it. In the column space, you're thinking purely in terms of linear combinations of vectors. With the image, you're thinking about the set of all possible outputs of a function, a linear transformation, but they are the same idea here. T is not onto. You know what onto means? Onto would mean every element of the codomain is the image of some element of the domain. For every b in R3, is there some x in R2 that gets mapped to it? T of x equals b. It's not going to be the case here. Linear transformations from a lower dimensional space to a higher dimensional space can never be onto. Can any such function be onto? Well, I'm not going to get into that. But certainly linear transformations are restrictive enough that they cannot be onto. Okay? In particular, as before, b, our right-hand side target vector, is not an element of the image because it's not an element of the column space. We have the exact same picture, except I just relabeled the plane to be the image of t instead of the column space. They are the exact same idea, just thought about in a different way. It's really the same picture with different labeling. By the way, with the subset notation here, I'm trying to emphasize that it's a subset but not equal to. The image is just a small part of the larger codomain. Hang with me here. We're almost getting to the punchline here. Just 3 more slides. And we want to remember what the punchline is. The punchline is we want to derive the normal equations. Okay? That's what we're working to right now. The first 3 slides of this part, we're just trying to talk about background ideas. So in summary, the system is inconsistent. There is no x, so that t of x, which equals a times x, equals b, this target vector. However, the geometry of the previous pictures, I'll go back and show you them in a minute here, should make it clear that there's at least one vector x. And here's the key, so that t of x, which equals a times x, is as close as possible to the vector b. I meant to make this boldface, but I forgot to. T of x equals a times x, which is in that plane, is as close as possible to b. Let's go ahead and look at the picture on the previous slide. There's some point in this plane that's as close as possible to the tip of b. In fact, it looks like it could be close to the tip of a2. Is it going to be the tip of a2? Probably not. But it looks like it's going to be close. In fact, if you draw a line from the tip of b down to the plane here so that I make an angle that's a right angle to make this line perpendicular to the plane, wherever this touches the plane, that will be the point in the plane, the point in the image, which is the column space, which is closest to b. We're going to call that point b hat. Hat. That seems familiar. We've been using hats in statistics. This is, in a sense, an estimate of B, you might say. It's the best estimate in the plane to B. Okay, we use hats in statistics for estimators that are trying to approximate different parameters. In this case, it's kind of like B is the parameter, B hat is the statistic. Such that, so there's a unique point, B hat, such that the distance between B and B hat, which you can also use this notation for, the norm of B minus B hat, kind of a generalization of absolute value. It's the length of the line segment between B and B hat, is minimized. Equivalently, the squared distance, the norm of B minus B hat squared, is minimized. If we in fact write that norm squared in an equation with more detail, it's a sum of squares, of errors. It's an SSE, which in previous lectures we've talked about minimizing with partial derivatives. But here we're minimizing it geometrically, and the key is we're going to talk about dot products very soon to relate it to certain products being zero, and that will help us derive the normal equations. Okay, that's what's about to come. Notice that I did put in the numbers here, 3, -4, and 2, which are the components of B. Okay, little inconsistent notation here. B1, B2, B3 are the components of B hat, whereas with the statistics they were the components of B. All right, but we are now relating this to SSE. 2 more slides here, hang on. Moreover, the vector B minus B hat will be orthogonal, perpendicular to the column space of A, which is the same as the image of T. In fact, B minus B hat is essentially that line segment that I drew in the picture, as long as you make the arrow point in the right direction. Let's go back to that picture. Which direction will it be? B minus B hat. If B hat has a tip right about here, say, B minus B hat is such that when you add that vector B minus B hat to B hat, you got to get B. B hat is an arrow going about like this. So B minus B hat has to be an arrow looking like this. Okay. It's going to be orthogonal to that plane, perpendicular to it. That's what that means. In other words, if A1 and A2 are the columns of capital A, then the dot product of both of those columns with the vector B minus B hat will be 0. Why? Because two vectors are perpendicular if and only if their dot product is 0, the number 0, not the vector 0. Okay. Focusing on these being non-zero vectors. Okay. They're perpendicular if and only if their dot product is 0. B hat, which again is in the image or column space, also has a name. It's called the orthogonal projection of B onto this image. Here's another picture, and here I drew B minus B hat in here as this green arrow going from here to here. And I also drew in a right angle there. So B is not in the image of T, which is the column space of A. It's not surprising because, again, the image is 2-dimensional, whereas R3 is 3-dimensional. That's why you don't typically have a solution. Typically, such a system is inconsistent. B hat is going to be the vector or point right here that is closest to the tip of B. B minus B hat, if you draw it so that its base is at this point, is this vector here. And we have this right angle. This is the last slide now. Okay, here we're coming to the punchline. Alternatively, you can think of these dot products being 0 in terms of matrix multiplication. A1 transpose times B minus B hat equals 0, and A2 transpose times B minus B hat equals 0. When you got the transposes there, when you multiply a row vector times a column vector of the same dimension, both say n-dimensional vectors, this would be a 1 by n matrix, this would be an n by 1 matrix. You can multiply them. You get a 1 by 1 matrix, which is a number, and it's the dot product of those two vectors. Okay, if you thought of them as, say, both column vectors. This product is the same as the dot product. You should already know that if you know linear algebra. Okay, you think about multiplying matrices, you multiply row times corresponding columns, you're really doing a dot product. So A transpose as a, well, for our example, this would be a 2 by 3 matrix times this vector, which is a 3 by 1 vector, gives a 2 by 1 vector, a two-dimensional vector of zeros. It's the zero vector in R2. You see where we're starting to move toward the normal equations here? A transpose is analogous to X transpose with the normal equations in statistics in our general linear models. We can rewrite this. We can use the distributive property to multiply the A transpose through the parentheses to get A transpose times B minus A transpose times B hat equals the zero vector. And then we can add A transpose times B hat to both sides and rearrange, if we like, to write this equation. This is starting to look really close to the normal equations, where again A is playing the role of capital X and B is playing the role of let's see, B hat is playing the role of B, and B itself is playing the role of Y. Almost to the punchline. If X hat in R2 has the property that A times X hat equals B hat, such an X hat is guaranteed to exist. Why? Because B hat is in the image of T, the column space of A. Then we say X hat is a least squares solution. This is really a definition of the original system AX equals B. And if you go ahead up here and replace this B hat with A times X hat, you get this equation, which, hey, that looks like the normal equations. In fact, it is. Okay? Again, the difference is, compared to the statistics, is just notation. Capital A here is the same as capital X before. This X is the same as B before, and this B is the same as Y before. Okay? X hat is a solution of this equation. If you replace this unknown X with the particular vector X hat, you will get a true equation. What's the answer? In this example, the least squares solution is found by multiplying both sides by A transpose times A, quantity inverse, on the left. If you multiply it on the left, you get just X. If you multiply it on the right, you get this times this. And you can check, it simplifies to negative 1/10 and 4/5, a two-dimensional vector that is the least squares solution. Moreover, this is not required, but just to emphasize, B hat itself turns out to equal this. You could double check that. You can take these components of X hat and make them weights or coefficients in the linear combination of the columns of capital A to get this for what B hat does actually equal. Okay. So that's the punchline. We're trying to get to the normal equations and do this to find the solution. Now there is a distinction here, another distinction between this and statistics. With statistics, with general linear models, the design matrices always have a certain special form, in particular always the first column as ones, where that's not the case here. Capital A is more of an arbitrary 3 by 2 matrix in this case. Let me end by showing you a spreadsheet as well. Maybe should have done that earlier. By the way, this Mathematica notebook does have stuff for inference in it, as well as the graphs I made, and my students should be able to do the calculations in Mathematica like I'm showing here to get the answers. This was for the stats example. We can solve for B0, B1, B2, and B3 in the stats example. I also have inference that can be done with linear model fit here. We're going to be soon getting into inference. Let's just end again by looking at the spreadsheet. So I have my x1 column, my x2 column, my x1 times x2 column, and my y column. Essentially, this is the design matrix. And if you are in Google Sheets or Excel on a PC, you have access to something called Excel Minor Analysis Toolpack. If you have Excel on a Mac, as far as I know, it's not available. That can do linear regression. And as I've shown you before, you want to go to the linear regression click the labels box first. Then when you do the X and Y range, make sure you include the labels. Highlight the Y's, including the label Y for the input Y range. Highlight all the X columns before you click the input X range, including the labels. And then we'll do an output range, say starting here. And I won't worry about residuals. Click OK. And you get some output. And the thing we're going to focus on here just for the moment to end this video is these numbers here are up to rounding the same numbers that we got before for B0, B1, B2, and B3 of our first example in this video. All right, I should have shown this earlier. All right, I hope you found that to be pretty cool. And my students, if you have any questions, let me know. Thanks for watching.